Okay, one more example from section 4.6. This one's talking about radioactive isotopes. It turns out that a radioactive isotope, that's an element that's radioactive, undergoes exponential decay, which means it decays like a exponential function. Exponential functions either grow if that growth rate is positive, or they decay if the growth rate is negative. So remember, we're talking about functions that look like this. If k is positive, the function grows. If k is negative, the function decays. It kind of disappears. And it's one of the phenomenal things about radioactive materials, that if you put a radioactive isotope in a jar, after a certain amount of time, you can measurably detect that there's less of that material in the jar compared to what you started with. So it follows this exponential model, and we're asked to answer a few questions here about this particular radioactive isotope. This is radium-226. Okay, so there's certain things we need to find. There's certain things we know. What they tell us in this problem is that it has a half-life of 1,599 years. Okay, and then they tell us after 1,000 years we have 1.5 grams of this material left. And the question is, maybe that material was trapped in some kind of container. If we had, say, 1.5 grams after 1,000 years, how much did we have to start with? And also, how much will we have after 10,000 years? Okay, so if you look at an exponential growth model, or decay model, we need two things. We need that initial amount, the initial population of radium, if you want to call it that, and we also need to know the exponential growth rate. Okay, so really what they're asking for in this first box is C. How much did we start with? Okay, well, to get that, we're going to have to kind of cheat a little bit. We actually have to find K first. Okay, and the reason for that is, if we don't know what K is, we really can't go any further. And they did tell us enough information to find K. They tell us that the half-life is 1,599 years. Okay, so let's start with that. The half-life is 1,599. Okay, what that means is that after 1,599 years, we'll have half of what we started with. Okay, so we can actually use that in the equation. If you look at our equation here, that gives us the amount after a certain time. If we start with C, we're going to have half of C after 1,599 years. Okay, so here's what that information tells us. When T is 1,599, we're going to go from whatever we started with to half of that amount. Okay, now it looks like we have two things in this equation that we don't know, C and K. But look, C is just multiplied on both sides. In that number of years, 1,599, we're going from whatever we started with to half of that amount. So we can actually divide both sides by C, and we get a new equation. Okay, 1/2 equals e to the power 1599 times k. Okay, so we can actually solve this for k, and it's pretty easy to do. We just take natural log of both sides. Of course, you remember now natural log cancels with e to a power, and we get, I'm going to swap sides here just to make it a little bit nicer looking, 1599 times k is equal to natural log of 1/2. Okay, so k is equal to natural log of 1/2 over 1599. Okay, and I didn't leave myself enough room here, so maybe I'll just go ahead and clear this out for now. Okay, so what is k? Well, we're prepared to say that now. K is approximately whatever the decimal version of this number is, and of course we're going to go ahead and write it as a decimal. Okay, so that exponential growth rate, the calculator is telling me negative 4.33 e negative 4, which is just negative 0.000433. Okay, if I move this decimal place to the right 4, 1, 2, 3, 4, I'd get negative 4.33. Okay, that's the calculator version of this number. Okay, so what do we do next? Well, having that growth rate really helps us a lot. So what we can do is say, really this model is c times e to the power negative 0.000433 t. Okay, And now we're going to be able to find the initial quantity because we know how much we have after 1,000 years. We know that when t is 1,000, we're going to have only 1.5 grams. So when t is 1,000, we'll have 1.5 grams. And if you look at this, we can solve this equation for c. Okay, in fact, it's pretty easy to do. C is just 1.5 divided by this big number. Okay, e to the power negative 0.000433. Okay, times 1,000. Okay, all I did here is I divided this big number, okay, to the other side of the equation. Okay, so I can get c. Okay, and again, this is something we'll have to get on the calculator. Probably the easiest thing to make a mistake on here is just, if you want to type this in all at once, just getting the parentheses right, but not too bad here. Negative 0.000433, okay, times 1,000. Okay, so here's what they tell me. About 2.323. Okay, and that will be grams. We're talking about units which are grams. Okay, now let's think about that a minute. Okay, the half-life is about 1,600 years. So after 1,000 years, we shouldn't quite have halved the amount of material we have. Okay, so does this make sense? We're starting with about 2.3 grams. Well, if the half-life is 1,600 years, in 1,600 years we'd have half of that, just like 1.1, 1.2 grams. So after only 1,000 years, we should have a little bit more left still. Okay, and so they told us 1.5 grams. So yeah, that makes sense. We're not quite down to half of what we started with. Okay, so the initial quantity, 2.323 grams. Okay, now with these problems, it's kind of like, once you get over the hump and get that difficult part done, it's not so bad to finish. Finally, they ask us, there we go, okay, the amount after not 1,000 but 10,000 years. Okay, well, if you look at what we found in that last part, we really know this exponential decay model. We know that it's y equals c, which is 2.323, we found that now, times e to the power negative 0.000434 t. Okay, so this is a question we can answer directly. After 10,000 years, okay, how much are we going to have? Well, we just have to put 10,000 in for t and see what we get. So on the calculator, we're going to have to type something like this in. That was 433. Okay. Okay, and get an answer. And, again, just to kind of put the answer in the right context, 10,000 years is like 6 times our half-life. So that means we will have halved the amount 6 times. Okay, so we started with 2 grams. We're going to have way under a gram, maybe like 1/10 of a gram or something, a lot less than a gram here after 10,000 years. Okay, because we've halved the amount about 6 times. Okay, so let's see here. Can I get this on the calculator? Okay, so I'm just going to type that in. Okay, yeah, and I do type it in, and I get about let's say 0.31 grams. Okay, and again, I'd say that makes sense because it's about six times of having our initial amount. 10,000 years is 6 times our half-life, so yeah, about 0.031 grams. Okay, quite a bit less than what we started with. In fact, almost nothing, relatively speaking.